Hello, and welcome to this next Tech Tip video 106, Understanding Head Pressure and Subcooling. In this video, we are going to focus on the condensing coil, its purpose, and how it functions to determine head pressure and subcooling. So here I have an illustration showing the compressor, the suction line, which is coming from our evaporator coil, our discharge line. We've illustrated the condenser coil in this manner to represent the volume that would be in a condenser coil and the two different parts of the condenser coil. Both of these represent the condenser coil. When we start the compressor, the suction line, which comes from our evaporator coil, begins dropping in pressure and refrigerant begins to flow. The compressor is compressing the refrigerant and pumping it. The refrigerant is a vapor and it is leaving the compressor into our condenser coil part A and part B. The head pressure is rising, and at this point we are not condensing any refrigerant. It is strictly a vapor. As the compressor continues to run, the suction pressure is going to decrease. Refrigerant flow is increasing. We are superheating our refrigerant even more in our compressor, and our head pressure is rising. The red represents the superheated high pressure vapor. The orange represents the desuperheating of that vapor, that we're reaching saturation temperature. Notice we do not have any condensing yet. Though we will be reaching saturation temperature, we have not condensed the refrigerant into a liquid. Head pressure is not as high as it normally would be. We're not condensing, and because of that we do not have liquid in this trap that is piped into our condenser coil. We need liquid here to create a barrier between the vapor and liquid so that we can subcool the liquid. So in this case we have no subcooling of our refrigerant. As we continue the run time, the suction pressure is dropping. On a fully charged system, we are going to reach the saturation temperature that is normal for this system, and we are going to have a superheated high pressure vapor. That vapor is going to reject its heat and reach saturation point, and that refrigerant then is going to reject its latent heat and condense into a liquid. The liquid will fill the subcooling trap in the condenser coil, which will allow a part of the coil, part B, to be able to reject more heat and subcool that refrigerant. Without having enough liquid to fill the subcooling trap, we will not be able to subcool our liquid refrigerant before it leaves our condenser. We have a high pressure superheated vapor. We have a saturation temperature. Until those temperatures exceed the temperature of the air going over this condenser, they're not going to reject heat. So as the head pressure increases, those temperatures are going to increase. That's going to increase the heat rejection ability of the condenser coil. Heat flow is directly proportional to the temperature difference between the air going over the condenser coil, the temperature of the refrigerant in the condenser coil. The greater that temperature difference, the greater the heat rejection. The other item that will affect head pressure is going to be the amount of air that is blowing over the coil. If the coil is dirty, if there is debris blocking the surface of the fins, or if there is debris that has accumulated in between the fins, that will hinder the airflow from circulating through the condenser coil and exiting, taking that heat with it. That is going to reduce the condensing rate of the refrigerant. So if we have a reduction in heat rejection, which creates a reduction in condensing, the head pressure is going to continue to rise until we reach a point that the condensing rate is matching rate of vapor being pumped in. We'll reach a point based on the equilibrium or the heat rejection rate. So, dirty condenser coil is going to give me a higher head pressure, air saturation temperature, and I'm going to have less subcooling of the refrigerant. So, when we are checking an air conditioning system, if our head pressure is higher than normal, if our subcooling is lower than normal, that would indicate a decrease in the efficiency of our condenser. If, on the other hand, have a low head pressure, zero cooling, may indicate low in refrigerant charge. Two other conditions that can occur have nothing to do with the efficiency of the condenser coil, but with liquid backed up into the condenser coil, taking up the volume needed to deal with the refrigerant that's being pumped in. And that would be a blocked liquid line which could be a restricted filter dryer or a restricted metering device. Either of these can cause liquid refrigerant to back up into the part of the coil and will take up volume in that condenser coil, reducing the volume available to deal with the vapor. This will cause an increase in head pressure, and because I have liquid taking up more space in my condenser coil, liquid is actually being cooled down closer to the ambient temperature of air blowing over the coil. So this can result in a very high subcooling, a high head pressure. It can also be due to an overcharge. Talk about some general rules of thumb.